Let's now get a better understanding of splitting, or understand the why behind splitting. Remember, our aim in these courses are to master organic chemistry, so in order to master it, let's see why we get the certain splitting patterns that we observe. And let's start simple here. Look at this molecule we have. Let's label this hydrogen right here as our A hydrogen, and let's label him as our B hydrogen. Remember, if we want to find the splitting for the A hydrogen, what we've learned so far, for the HA hydrogen, his N value equals 1. There's only one B hydrogen. So using the N plus 1 rule, N plus 1 equals 2. And we know that we should observe a doublet for the A hydrogen. But the question is, why a doublet? Well, let's get a better look at this here. Let's put our molecule in the NMR. And let's get a blow-up view of our molecule like this, and let's separate things so we can clearly see all the atoms. And let's put our labels back on. This is the A hydrogen, remember, and we're calling this our B hydrogen. Remember, the hydrogen atom could be thought of as a magnet, and let's say it's a magnet pointing in this direction like this. And let's focus on the A hydrogen. Again, he could be considered a magnet. Let's just focus on one of the A hydrogens, and he looks like this. Remember, all three A hydrogens are equivalent, so we're only focusing on one for right now. And of course, we know how it works. We turn on the NMR, and the B applied magnetic field is generated. Also, let's place our formula here that helps us out with shifting. The B effective equals B applied minus B local. So here we go. Let's focus on that HA hydrogen. Again, why is he a doublet? Well, take a look at the B hydrogen. Remember, the B hydrogen is the one that's going to split his signal. We talked about before, when you turn on the magnet, the H atom has two possibilities that he can get stuck in. Remember, one, he can get stuck in the high energy position, which is, of course, remember, the beta position. That's possible. Let's pretend that that happened in this particular case. And let's see how that would affect the A hydrogen here. And let's consider this green bubble right here. That's representing that hydrogen's B effective. So if the B hydrogen gets stuck in this orientation, notice its direction compared to the B field applied by the NMR. It's pointing in the opposite direction. So the B hydrogen's magnetic field is going against the B applied field. If it's going against it, then notice in our equation, the B applied would be lessened. And lessening the applied field would cause the A hydrogen to have a lower B effective. And remember our principles from before, if you have a low B effective as a hydrogen, you are going to require less energy to bring you into resonance, and that means the more upfield your peak is going to appear. So let's look at the NMR spectrum here, and let's place this situation on it. Let's say that this peak right here is for this particular situation. Now, let's go back and start over from the beginning here. There's another possible situation in this case. This time, let's say this happens right here. Our B hydrogen, after we turn on the B applied field, let's say he happens to go with the magnetic field in the alpha spin state. That, remember, is a possible situation. But let's see how this situation affects the A hydrogen. And more specifically, let's see how it affects his B effective. Notice, since now the B hydrogen is going with the applied magnetic field, then that means it's adding to the B apply field. And additive means that the B apply field would be increased. And according to our equation, increasing that value will increase the B effective as well. That means for this particular situation, there'd be a greater B effective. And remember, the greater the B effective, the greater the energy it takes to bring that hydrogen into resonance. And that in turn means the peak would be more downfield. Since this is technically a slightly different environment for the A hydrogen, then that slightly different environment would have its own associated peak to it. Therefore, we would observe a doublet for the A hydrogen. So here's all I'm trying to get across to you. When we put our sample molecule in the NMR, we turn on the applied magnetic field like this. We're saying that the B hydrogen could possibly orient itself this particular way by random chance. That in turn creates a certain magnetic environment for the A hydrogen. And that magnetic environment has its own peak associated with it. But remember, that's only one possible situation. Going back, again, if we turn on the magnetic field like this, then it's also possible that the B hydrogen could orient itself with the magnetic field. That's going to create a certain magnetic environment for this A hydrogen as well. But the point is that the environment is going to be different from the previous situation. And remember, a hydrogen in a different environment is going to have its own signal or peak, which would be this signal right here. But notice, here's the thing. Those two different environments, although they are different, they're not extremely different. That's why the doublet peaks appear very close to each other. And that's why we have to turn up the resolution on the machine so that we can actually distinguish those two doublet peaks from each other. Which is great because we wouldn't want to perceive them as two separate peaks for two different hydrogens. Now, if you understood that, let's now do the same type of analysis, but this time for the B hydrogen. So here he is. Remember, we're calling this the B hydrogen, and there's only one of them, and let's just say his magnetic orientation happens to be like this. Now, for the A hydrogens, notice, remember, there's 3 A hydrogens. So this time, let's show all 3. And let's just say, by random chance, all 3 happen to have this orientation. And then remember, the next thing we do is turn on the NMR and release the applied magnetic field. So now this time we want to focus on how these A hydrogens affect the B hydrogen. What are all the A hydrogen possible combinations that could possibly affect the B hydrogen? Let's run through them. One situation, possibly, is that all of them, all 3 A hydrogens, align themselves in the beta spin state. How would that affect our B hydrogen? What environment would that place him in? Well, since all 3 are going against, it would lessen the B apply field. And a lessened B apply field would mean a lessened B effect field on the B hydrogen. But for now, let's just look at our NMR spectrum and say that situation would correspond to a certain peak because it's a certain magnetic environment for the B hydrogen. But what's another possibility for these A hydrogens? Instead of all 3 randomly pointing up, maybe when we turn on the NMR machine, 2 went up and one of them ended up spinning down. That would put the B hydrogen in also a slightly different environment. And let's just say for that situation, that particular environment would cause this peak right here. But there's even another situation. What if instead of 2 hydrogens going in beta and 1 going in alpha, let's say 2 are in the alpha position and 1 is in the beta position by random chance. That's a unique electronic or magnetic environment, so that would correspond to a certain signal on the NMR. And notice there's only one last possibility here. That means all 3 hydrogens point in the alpha state. That is again a unique environment that is contributing to the B apply field, so we should expect this situation to make the B hydrogen peak more downfield, like this right here. Notice what you see here is a quartet. And remember, if we were to just take this molecule, focus on the B hydrogen, and apply the n+1 rule, for the B hydrogen he has 3 neighbors, so his n value equals 3, and of course 3 plus 1 equals 4, the n+1 rule would predict a quartet. But now we understand why the signal ends up being a quartet. There's also something else that we can actually explain about the quartet. For instance, why does it have the shape that it has? Why are the 2 peaks in the center taller than the 2 peaks on the ends? That can be easily explained. Again, let's think of our hydrogens as magnets. We have the 1b hydrogen magnet and the 3a hydrogens. And again, let's place our bubble here. This is our B effective for the B hydrogen. And we just learned that the quartet is generated because there's different possible orientations for the A hydrogen. We saw that all three, remember, could point upward. That situation would be this peak right here. But we also saw that one of the hydrogens could be pointing down and the two others point up. That would be this peak right here. However, that's not the only way we can orient two up and one down. The case we're looking at right now, it's the two left hydrogens are up and the rightmost hydrogen is pointing down. But it also could be this way. The left and ultimate right hydrogens point up and the middle one points down. However, in terms of an electronic environment or magnetic environment, that would be really no different from the two on the left pointing up and the right pointing down. Both of these situations are really just, again, two up and one down. So either situation would create the same magnetic environment for the B hydrogen. And there's also another situation for two up and one down. It could be something like this. The two right hydrogens are up and the leftmost one is down. All three of these possibilities create the same magnetic environment. And since there's three possibilities for this situation, and only one possibility for the first peak we looked at, that's why when we look at the NMR at a quartet, the ratio is always going to be 1 to 3. Or we can say the relative heights are going to be a 1 to 3 ratio. Now, taking this logic further, we can explain the remaining two peaks here. Let's go back to our A hydrogens. Remember, instead of 2 up and 1 down, remember, it could be 2 down and 1 up. That would correspond to this peak right here. And just like the peak before, there's three possible situations that generate 1 up and 2 down. There's this situation right here. That's also 1 up, 2 down. And so is this, also 1 up and 2 down. And because they're three, that's why the height of this peak is the same as the second peak. And then this brings us to the final situation. All A hydrogens are pointing downward. For this, there's only one possible situation. There's no other way to orient all of them downward. So since there's only one possibility, that's why our last peak has only a relatively 1 unit height. This peak would simply be 1/3 of the two middle peaks. We can also apply this same logic to the A hydrogen. For instance, why for the doublet for the A hydrogen, why are the peaks the same height? Let's focus on him for a second. Remember, we saw before he would be a doublet. And let's turn our hydrogens into our magnetic versions like this. And now let's focus on the B effective for the A hydrogen. Remember, his magnetic environment is being influenced by the B hydrogen. But since there's only one B hydrogen, there's less possible magnetic environments. Remember, there's only two. The B hydrogen could either orient itself up like this, and that would give rise to, let's say, this peak, or the B hydrogen could be down like this, and that would give rise to this peak right here. Both are equally likely, so both situations have a 1-to-1 ratio, which means the peak for the doublet is also a 1-to-1 ratio. It's very important that we pay attention to this, because think about it. Let's say you're on your orgo exam and you are looking at an NMR and you happen to see a peak that looks like this. If we didn't know the relative heights, one might think that that peak right there is a quartet because they see 4 peaks. But remember, we know an actual quartet looks like this. And also, we know why it looks like that. So we wouldn't see the peaks on the left as a quartet. More likely, we would see it as a doublet next to another doublet. And we would perceive this as the quartet. So we're doing more than just counting the number of peaks split. we're also paying attention to relative heights.